Good day. So in this video, I'm going to show you two examples of applications of integrals in the context of economic statistics. I'm pretty sure that you have encountered these problems already, particularly problems involving solving for expected values in some other moments given a probability density function, given of course the characteristics of the random variables of the said function. So we have two examples here. One that involves a single, basically univariate density function, and we have another example that involves multivariate or bivariate density functions. I'm pretty sure you have encountered this already. So statistics typically rely on integrals because when we look at distribution functions, like your normal, your bell curve, your normal distribution, we are actually interested in the probability. Right? And these probabilities, especially for continuous random variables, the probabilities here involve areas under the curve. So solving for areas under the curve require some skills on integral, skills from integral calculus. All right. So let's try to solve one univariate example. So suppose you have your PDF given by f of x, pretty simple example, f of x, you have 4x cubed, and let this be defined over the range 0 to 1, 0x 1. Right? So we're restricting the random variable x, right, to vary over 0 and 1. And this is a corresponding PDF wherein we can solve for the probability of x being between certain values within this range, or we can solve for the average or the expected value and its variance. Right? So to solve for the expected value, you already know this, the expected value of a random variable x, right, is given by the integral, not this one, but let's use this. It's basically an example of a definite integral. So you have 0, 1, right, x times f of x dx, right? So we're basically using f of x as weights, right? Given its density function, f of x, this is the weights, and x would be all of the possible values of x, and we know that's defined between 0 and 1, right? So average and the expected value of x here would be just the integral. You can copy this. It's just the integral of x times what's f of x. F of x is 4x cubed dx, right? Now this is not so much. This is not too complicated because we can just factor out 4. We can factor out 4, and then we can solve for the integral of the resulting function, which is x raised to the fourth. So e of x will be equal to the integral of, let's put 4 here. You have 4 times the integral of x to the fourth. Right? This changes, so this becomes x to the fourth dx. All right. Now, by power rule, from integral calculus, the power rule here is that we'll need to add 1 on the exponent. Right. So this becomes x to the fifth, and we need 1 over 5 here. Right. Now, of course, to check, let's copy this. To check, you can just take the derivative, right? So here, e to the x would be equal to 4 times, let's try c dot, 1 over 5 x to the fifth, right? Evaluated between 0 and 1, right? It's evaluated between 0 and 1. And if you can check, you just take the derivative of this 1/5 x to the fifth, and you will get the original function, which is x to the fourth, right? So take the derivative of this, right? Take the derivative of this respect to x. So this becomes, well, 5 cancels out. You have x to the fourth. Right? So when we evaluate this between 0 and 1, right? So this becomes 4 times 1 over 5th times 1 minus 1 over 5th times 0, basically. So the last term cancels out. Therefore, the mean or the expected value of this random variable, given this conditional density function, given this density function rather, is 4/5, right? Because this cancels out. Right? Now, we will save this. We will save this result later when we try to solve, and we will use this when we solve for the random variables variance. All right. So the variance of x is given by this formula. Right? I'm pretty sure you already know this, times the square of e to the x. So that's your random. That's your variance. That's a variance of the random variable. We already know what e to the x is, so it's just a matter of plugging this later on. But we're concerned with e to the x squared. Now, to solve for the expected value of x squared, same formula. Let me just copy this, right? And try to change a couple of things. Okay. So instead of e to the x, we have e to the x squared. And this, of course, becomes x squared times 4x cubed, right? Now we can factor 4 again. We can factor out 4 again. So you have 4 times x to the 5th to the 5th dx, but this is a simple function, so this just becomes 4 times 1 over 6 x to the 6th. All right. Again, evaluated between 0 and 1. Now, since this becomes 0, so the last term cancels out, you're left with 4 over 6. All right. You're left with 4 over 6. So that's the first term. Now what now is the variance of x? So the variance of x is 4 over 6 minus 4 over 5, 4/5 squared. All right, and that's just 4 over 6 minus 16 over 25, right? And you're left with 4 over 150. You can simplify this. Then the variance of this random variable is 2 over 75. Take note that the variance is always and supposed to be always positive. All right. So if you're getting a negative variance, then it means that you have done something wrong in your calculations. So I'm pretty sure you have already encountered that in your econ stat. But just a reminder that when you're talking for the variance of any random variable, it's always positive, because you're looking at the spread. You're basically looking at the distance of your random variable. You're looking at the spread of your random variable with respect to its mean. So it's a distance measure. It's sort of a distance measure. So that's your application of integrals for a univariate random variable. Now let's try to complicate things a bit, right? And let's try to look at a bivariate random variable whose joint distribution function, you know this, the joint distribution function is given by lambda squared, right? E raised to negative lambda x plus y. Right? Suppose you have that joint distribution function. Now the next question is, verify, and this one's easier because you already know the mean, but let's just verify, right? Verify that the mean of x is given by 1 over lambda. So simple exercise. Okay. So first, before we can solve for the expected value of x, we need to get the conditional distribution or conditional PDF for x first. So we cannot use this joint. We cannot use the joint distribution function when we wanted to solve for, say, the expected value of one of the random variables. So we need to change this. We need to extract the conditional density function from the joint distribution function. So to extract f of x, we need to get let me just specify that x goes from 0, right, and y also goes from 0, right, so positive, right. So to extract f of x, right, f of x is obtainable by getting the integral of the joint density function, right? And of course, this runs from 0 to infinity. And let's copy this. Right? So you're getting the integral of the joint density function all over y to get x. Similarly, if you wanted to get the density function of y, you need to get the integral of the joint density function with respect to x, so all over x. So this time we just needed f of x. So we'll take the integral of the joint density. You'll get the marginal, you call this the marginal density function by taking the integral of the joint density function all over y. Okay? It's for all values of y. Okay. Now we can just copy this. All right. So let me just copy this. And let me just copy this expression here. Okay. And we can factor out some things. Now take note that taking the integral of a function with two variables like this one is sort of similar to taking the derivative of a function with multiple variables. All right. So for instance, if you wanted to get the integral of this joint density function with respect to y, all of the x terms here are considered constant. So we can move some of the terms here outside the integrand. So this is gonna look like this. All right. So we can factor this out. I'm gonna do this because it's gonna be easier later on. But let me factor out lambda e raised to negative lambda x, right? And let's leave out another lambda here, right? It's gonna be helpful later on, right? So now that it's already a function of lambda y, we can actually by inspection, by taking note of the rules of integration and rules of differentiation, especially when it comes to exponential functions. By inspection, you can actually get the integral of this term, right? You can actually get the integral of this term. If you wanted to do it the long way, then you can use integration by substitution. That's perfectly fine, right? But obviously, when you look at this expression, this is equivalent to lambda. And I'm adding this here, no? So you have lambda e raised to negative lambda x. Okay. But here you have e raised to negative lambda y. And we will evaluate this between 0 and infinity. Right? Note, take note, or well, this is negative, supposed to be negative. Right? Now take note that if you take the derivative of this expression, you will get lambda with respect to y. You'll get lambda e raised to negative lambda y. So by inspection, this is actually correct. It's supposed to be correct. Okay. Now, how do we evaluate this between 0 and infinity? If you have this expression that requires you to get the integral or evaluate this integral function between 0 and some infinity, some variable, or we let y approach infinity, we'll need to use limits. All right. So let me just copy this again. And this expression is going to be equal to the limit, right? Since you have an infinity here, we're going to push this bracketed term towards infinity, right? So this is going to be the limit of negative e raised to negative lambda y as y approaches infinity, right? Minus, and incidentally, this becomes a positive sign, right? Because this is negative, you subtract another negative term, then this just becomes positive. But e raised to 0, right? We plug in 0, in this expression, this becomes what? Well, e raised to 0 just becomes 1, right? So this becomes positive 1, okay? And therefore, let me just add f of x now here, since we already got we're about to get, the marginal density function, right? Take a closer look. So this is a fraction, basically. This is equivalent to negative 1 over e raised to lambda y, right? So if we let y approach infinity, the denominator will increase without bound, right? And therefore, the entire term becomes 0, right? So then the marginal density function of x, right, from the joint PDF is equal to lambda e raised to negative lambda x, right? Now we can solve for e of x using this marginal density function. So we now know what f of x is, right? So f of x is equal to negative lambda e raised to negative lambda x. All right. So e of x, laying out the formula, e of x is the integral of x times lambda e raised to negative lambda x dx, obviously dx. And since x increases without bounds, so you have 0 to infinity. Okay. Now we can factor some things out. So let's leave out lambda for a bit, right? Let's factor out lambda to make it easier to compute. We will use that again later. So this becomes x times e, so you have lambda here. You can factor out lambda. Right, so let's focus on this integral first, right? Let's focus on this expression first. Now, this is not a straightforward, there's no straightforward solution for this because you're gonna need to use integration by parts. All right, we're gonna use integration by parts. Integration by parts is useful when you have a product function or a product of two functions, right? Like this one. So you have two functions. You have x and you have e raised to negative lambda x. Two functions, and you cannot really take the integral of this function in a straightforward manner. So we're going to use integration by parts. So where does this principle of integration by parts come from? So basically, it's using the product rule of differentiation. So we know that when you take the derivative of, let me just mark this as integration by parts. So we know that when you take the derivative of a product of two functions, the product rule states that you take the derivative of the second function first, or regardless. So you have u dv, and you take the derivative of the first function. So you have v du, right? Now, taking the integral of both sides, right, you have the d cancels out on the left-hand side. So you have the integral of, so uv, the d cancels out on the left-hand side. So you just have, we're left with uv equals integral of u dv plus the integral of, this is actually useful when you try to solve for the integrals. It's useful to write this down. Okay, so you have v du. Now it's your choice. It's actually a matter of preference. Where will you assign x in the second part, which is e negative lambda x dx, right? So normally we assigned it here in the first function, and therefore to get the integral of u dv, right, you're gonna need to, well, let's copy this. This translates to u dv equals uv minus v du. Okay. So it's a matter of assigning which one will be the function u and which one will be dv. All right. So you have this. So we have this integral. Let's solve for this. Okay. Using this principle, using this, using integration by parts. All right. So we let u equal x. Right. So that would be the u function, and then we'll let dv be the second portion of the integral, which is e raised to negative lambda x dx. Right? Now, since we already know what u and dv is, it's just a matter of getting what v is, so what's v, and solving for v du. Right? So we can do that by taking the differential of u and solving for v from this expression. So du is obviously going to be equal to dx, right? And v, by inspection, you'll have negative 1 over lambda, 1 over lambda e raised to negative lambda x. You can double check and see that when you take the derivative of this v with respect to x, right, you will still get e raised to negative lambda x. Now it's just a matter of substituting this component. So uv, sorry, an integral of u dv, which is essentially this expression, is now equal to uv, which is equal to negative 1 over lambda x e raised to negative lambda x, right? So this is your uv, right? U times v minus what's v du, right? So the integral, or we need to get the integral of v, this negative lambda. Let's copy this. Okay. dx, right? Which is du. So this is v times du. Right. So just to avoid confusion, let me just copy this formula again in the previous slide. So it's a matter of substitution, right? It's a matter of substitution, which is u. So you have which is u, which is assigned, which function is assigned to v, which function is assigned to v, and which function is assigned to du. And you can get it all from here, right? You can get it all from here, hence this expression. Right? That's just a matter of solving this. It's just a matter of solving the remaining integral. So let me just copy this. Okay. And by inspection again, right? And we can actually factor this out. Right? Let's try to factor this out. So this becomes, copy this. Let me factor this negative lambda out. So you have positive 1 over lambda You have 1 over lambda, the integral of e raised to negative lambda x dx, right? However, again, by inspection, this becomes 1 over lambda, right? Negative 1 over lambda, negative 1 over lambda e raised to negative lambda x. So this becomes, so basically this entire expression, right? This entire expression, which is our u dv, is equal to negative 1 over lambda x e raised to negative lambda x plus, sorry, plus 1 over lambda times negative, or if you're not comfortable, you can just move out the negative sign already. So this just becomes 1 over lambda e raised to negative lambda x. Okay. Now, recall that we still have this lambda, right? So we already know what this is, right? We already know what this is, and this is given by negative 1 over lambda x times e raised to negative lambda x minus 1 over lambda times 1 over lambda e raised to negative lambda x. So remember that we still have the lambda. So if we return this lambda, right? When we return the lambda, e of x then becomes xe, right? If we return the lambda in this expression, lambda will cancel out. So you have xe raised to negative lambda x minus 1 over lambda raised to e raised to negative lambda x. Okay. Now, if you're more comfortable, you can factor this out. So uh, you have x minus 1 over lambda e raised to negative lambda x. Okay. Now, we're not yet done because we still need to evaluate this between between 0 and negative infinity, right? Sorry, between 0 and infinity. So evaluating this between 0 and infinity, let me copy this entire expression again. Evaluating this between 0 and infinity, we need to use again limits. So e of x is equal to the limit of this expression as x approaches infinity minus well, you substitute 0 here, you'll just have negative 1 over lambda, right? Which is equivalently equal to the limit which is basically equivalent to the limit of okay, fine. the limit of this term, bracket term, x approaches infinity, plus 1 over lambda. And here's the thing. This is a fraction, right? And when you let x approach infinity, you'll have an indeterminate form, right? You'll have an indeterminate form, and this is practically equal to e of x times the limit, or equals to the limit of fraction, which is x minus 1 over lambda over e raised to lambda x, e raised to lambda x as x approaches infinity. Oops. X approaches infinity plus 1 over lambda. All right. Now, by inspection, since this is in the indeterminate form, you can use L'Hopital's rule. Now we'll just have to use L'Hopital's rule once. We'll have to use L'Hopital's rule once, right? And this becomes 1 over e raised to negative 1 over lambda e raised to negative raised to lambda x, right? So the denominator will be increasing without bound. The numerator will be constant at 1. So therefore, this limit expression will cancel out, become 0, and therefore it proves, we can now verify that indeed the expected value of x given the joint density function is equal to 1 over lambda. Oops, 1 over lambda. Now, you can do the same. You can do the same for y. Take the expected value of y. Notice that the function is symmetric, right? And therefore, you'll be getting the same functional form for the marginal density of y, and you will get exactly the same. You get exactly the same expected value for y. Right? So this video concludes here. Well, if there are any other concerns, you may want to revisit, or you want to visit our discussion threads, right? You may also want to practice using some problems, involving integrals. Thank you so much for listening.